Hello everyone. Today we're going to talk about density and IR exposure. We talked a little bit about this right before we ended our last quarter, but I wanted to, before we start on contrast, I wanted to review density and IR exposure with you. So remember, when we talk about density or contrast or detail or distortion, we're really talking about those elements that form the radiographic image. Density and contrast are referred to as the photographic properties, whereas detail and distortion are referred to as the geometric properties. So when we talk about density, and that's what we're talking about in this session, density was originally defined as the viewable result of a film's response to exposure. So, for example, if you had a film that was too dark, we would say that that film is overexposed. If we had a film that was too light, we say that it was underexposed or had inadequate exposure. Now, in the film environment, the film screen environment, if we got an overexposed or an underexposed image, the only thing that we could do basically was go and repeat the film. Today, with the digital imaging equipment that we have today, if we over or underexpose a little bit and we're still within the correct exposure range, we can use the computer to help us out to give us the proper amount of brightness on the image. So in the digital environment, IR exposure is the more appropriate term. Carlton makes it a point that brightness and density are not interchangeable terms, although some authors you're going to find do combine the two. They talk about brightness, IR exposure, and density almost as being the same thing, and basically they're really not. If we think about it, when we're talking about IR exposure, we're talking about the amount of radiation that's reaching the detector. And that amount of radiation reaching the detector is influenced by a lot of different factors. The mass that we use, the kVp we use, the distances that we use, and so forth. Once the detector receives a certain quantity of radiation, the computer then is able to take that information and formulate an image. When the image comes up on the screen, then we, the technologist, have the ability to change the brightness of the image, but what we're changing is a monitor control. So brightness is a monitor control that can be adjusted to change the lightness and the darkness of the image, regardless of the IR exposure. Remember, the IR exposure is the amount of radiation that the detector is receiving. And once that IR has received a given amount of radiation, the image brightness then can be changed by adjusting what we call the window level. We're going to talk about the window level and the window width in much more detail when we get to our class on digital imaging. There's a main controlling factor when we talk about density or IR exposure, and that main controlling factor is milliampere seconds or mass. If we increase the mass, what does that really mean? It means that we're creating more photons, and those photons, because there's more of them, they can reach the detector and increase the amount of exposure. Now, when we were utilizing film, if we increased the mass, we took the image, we took the film to the darkroom, we put it through the processor, and if I increased the mass from an original film that I had, I would come out with a darker film. So kind of the same thing, okay, in the digital world. If we're increasing mass, we're increasing the amount of exposure that that detector is receiving. And in the film screen world, if we increase the mass, we were increasing also the amount of photons that the film and the screen were receiving. Now, when film screen systems were used, in order to see any visible shift in density at all, you had to change your mass by at least 30%. If you didn't change your mass by at least 30% from your original mass that you used, you really wouldn't see a visible change in your image. Now, the rule is essentially true for digital imaging as well. Most exposure indicator systems are set so that an acceptable range includes 33% on either side of the ideal 1 milliroentgen exposure required by the detector. What that means is that if our detector can receive 1 milliroentgen worth of exposure, it has enough information to take that radiation, take those components that make up the image as far as the detector is concerned, that radiation hitting the different parts of it, and formulate an image. Now, if we use too much radiation, more than 1 milliroentgen, we can subtract off density. If we don't use enough radiation to get that 1 milliroentgen, well, then we have a little bit of a problem, because then our film starts to get a little bit grainy. We start to develop quantum model. But you have a mid-range. You have a number. Like in the Fuji system, for example, that number is called our S number, right? And when you take an image, and you probably have seen the techs do this, they look at the number, right? And they want that number to be within a certain range, okay? And that range is going to be between that ideal 1 milliroentgen, whatever that number would be, 33% on each side. The density mass reciprocity law, we've talked a little bit about this already. Remember that density should remain the same as long as the same mass value is used, regardless of the MA and the time combination. So if we take a look at this example here, like if we took 300 MA at 100 milliseconds, and we calculated the mass. Now remember, we're dealing with milliseconds, so did you remember to divide the 100 by 1,000, right? Because it's milli. Well, if you take that then and you multiply that after you've divided the 100 by the 1,000, multiply it by the 300, you end up with 30 mass. And let's say that that 30 mass then is our amount of density or IR exposure. We'll call it X. Well, if I doubled my MA to 600 and I cut my milliseconds in half, and if I multiplied it out, I'd still come up with 30 mass. Well, theoretically, then I should still get the same amount of density or IR exposure. If I bumped it up to 1200 MA, but I dropped my time value down to 25 milliseconds, and I did the math, I'd still come out with 30 mass, okay, giving me X amount of density or IR exposure. So once again, as long as you're getting the same mass, regardless of the MA and time combination that you're using, you should be getting the same amount of density or IR exposure. We're moving to kilovoltage as an influencing factor. So our main controlling factor of IR exposure or density was mass. Kilovoltage is said to be an influencing factor. So both the quantity and the quality of the beam will vary significantly with changes in kilovoltage. Why is this? If we increase the kilovoltage, more photons will penetrate the part to reach the IR, because we know that as we increase kVp, we increase penetration. Well, if more photons are reaching then the detector or the IR, we're going to increase the amount of IR exposure or density. If we decrease the kilovoltage, we're going to have less photons that are going to be penetrating through the part. And this then would decrease the IR exposure or density. The 15% rule, we've talked about this. Remember, if we increase our kilovoltage by 15%, we're going to double the amount of exposure reaching the IR. And conversely, then, if we decrease by 15% in our kilovoltage, we're going to half the exposure to the IR. We want to keep in mind down at the bottom there, the use of the 15% rule will change the initial contrast of the image because KVP is the primary controlling factor for image contrast. So that's why we try not to, if we've got an image that's too light or too dark, to manipulate the KVP. We'd rather change the mass. Sometimes we can't change the mass, and we have to change the kilovoltage. Let's take a look at this example here. So if we had an original technique of 80 at 20, let's say that gave us X amount of IR exposure or density. If I use the 15% rule and I take that 80 and I multiply it by 0.15, or 15% of 80, I end up with the number 12. If I took that original 80 and I added 12, and I kept the mass the same, I would end up doubling or getting 2 times the original IR exposure or density. If I went back to the original number of 80 and I subtracted now the 12 to get 68 and left the mass still at 20 again, I'd get 1/2 of the original IR exposure or density. Effective generator phase on IR exposure. We talked a little bit about this, and I said that it really probably isn't going to make too much sense to you right now because you don't know what generator phase has to do really with creating your image. We'll get more into that in physics. Think about it right now as a single phase generator as being, and I'm going to put this in quotes, weaker than a high frequency generator. So think of the single phase generator as weaker and the high frequency generator as stronger. Okay, not the best terms, but they're terms that make it easy for you to understand, given that you don't understand yet the physics behind the phasing of the generator. So when converting from single phase to high frequency, so what did we say? Single phase is weaker, high frequency is stronger. So to maintain IR exposure, you decrease the original mass by half because single phase is weaker, high frequency is stronger, so you can decrease your original mass by half. So if you had original technique of 80 at 10 mass on a single phase piece of equipment, you got X amount of IR exposure. And then you're going to a high frequency piece of equipment, you could actually then cut that mass in half, so go to 80 at 5 to get that same amount of IR exposure. Conversely, then, if you're going from a high frequency generator, we're going to say that's the stronger one, to a single phase, which would be the weaker one, okay, to maintain the IR exposure, you double the mass. So once again, if I had an original technique, let's say on the high frequency I was using 80 at 5 mass, that would give me X amount of IR exposure. But because we're going to a weaker generator, high frequency to single phase, the new technique for the single phase is I'd have to use 80 at 10 mass. I have to double it to get that same amount of IR exposure. Other influencing factors on density and IR exposure. Well, what can we change when we change a technique? Well, one thing we can change is the focal spot size. And if I go from small focal spot to large focal spot, it really shouldn't do anything to the density or IR exposure. You'll see that when we get into detail, that has a big effect. The changing of the focal spot will have a big effect on detail, but not so for density. The anode heel effect. Carlson says that there's really no change. Now, you might say, well, wait a minute, isn't the beam more intense on the cathode side versus the anode? And it is, but if you you kind of look at it in an overall image, it really doesn't change the density that much. So Carlson considers the anode heel effect as having really no change on IR exposure or density. Now, SID, this is going to have an effect on your density or exposure. If I increase the SID, okay, so I've got a technique, and let's say I'm going from 40 inches to 72 inches, I don't change anything, I'm going to decrease my IR exposure or density because of the effects of the inverse square law, how that beam is going to diverge out. And think about if you had the cassette right in the middle or the IR in the middle and then you're diverging out, you're losing all that radiation that's now on the outside borders of your image receptor. If I decreased my SID, so I was at 72 and then I came down to 40, but I didn't change my technical factors, well, now I'm going to increase my IR exposure or density because my beam is closer, it's more intense. So to maintain IR exposure or density when SID changes are made, use the exposure density maintenance formula. So we talked about this formula before. So it would be mass 1 over mass 2 equals D1 over D2 quantity squared, or you could say D1 squared over D2 squared. So as an example, if a satisfactory exposure is obtained at 40 inches using 30 mass, what mass will be required to maintain the same exposure at 72 inches? So before you do any math, think to yourself, all right, I was at 40 inches and I had 30 mass. Now I'm going to move my tube further away. My beam's going to diverge out more, okay? So to have the correct amount of exposure on my image receptor, I'm going to have to do what to my mass? I'm going to have to bring it up. So remember the formula is original mass over new mass equals original distance squared divided by the new distance squared. So I would take 30 over x equaling 40 squared over 72 squared. I cross multiply, I end up with 1600x equaling 155,520. I use my algebra dividing both sides by 1600 to isolate x, and I would end up with 97.2 mass. So to get the same amount of exposure going from the 40 inches now to 72 inches, I'd have to increase my mass pretty significantly to 97.2. There's one more distance that is talked a little bit about in the book. I just want to mention it here, OID. So when we increase our OID, which is bringing the part further away from the image receptor, what's going to happen? Well, what's going to happen is more scatter is going to miss hitting the image receptor. Because we're at a further distance, these photons are going to scatter outward and they're going to miss the image receptor. Well, always keep in mind that even though scattered photons are not good photons, not good radiation, it's still radiation. So if some of those photons now are missing the image receptor, density would decrease. So as OID increases, density or IR exposure decreases. Talk a little bit about filtration. When filtration, remember filtration is like metal, usually aluminum, is inserted into the path of the beam, the overall quantity of photons that strike the detector is reduced. So just think about it. You've got our X-ray tube, photons are coming down, there's a piece of metal in its path, that metal is going to absorb the photons, and you're going to get less photons then that are eventually going to strike your detector. All types of filtration, whether it's inherent, added, or the combination giving you the total filtration, all those types of filtration alter IR exposure or density. So we can say that as the thickness of the filter increases, the IR exposure or density decreases. Beam restriction. When we say we restrict the beam, that's just a fancy way of saying we're collimating the beam. And remember, if you increase the collimation, you're making your field size smaller. Okay? So if I said to you, go into a room and collimate more, what would that mean? It would mean that you would take your field size and you would make it smaller. So remember, scatter radiation reaching the IR increases the IR exposure or density. If the collimation is increased, so we get a smaller field size, think about going from a 14 by 17 down to an 8 by 10. Because you're irradiating less of the body, you're going to get less scatter. Okay? And remember, even though scatter isn't good density, it's still density, right? So if collimation is increased, scatter reaching the IR then would decrease. There's less of it. And IR exposure or density would also be decreased. Okay? So there probably will be a question on the registry, something to the effect if you radiographed a body part, and let's say it was an abdomen, and you used a certain kilovoltage at a certain mass. So you were using a manual technique. If the doctor told you to go into the room then and collimate down to the area size of an 8 by 10, perhaps over the gallbladder, or an 8 by 10 over the bladder, you'd have to actually increase your technique, because what you're doing now is you've gotten rid of all of that scatter that, even though isn't good density, it's still density. And if I didn't increase my technique, I'd get an image that would be too light. So it's kind of hard to understand, but just think about that. When I collimate down, I'm getting rid of scatter. Scatter, it's not good density, but it's still density. So if I collimate down and I'm trying to maintain a certain amount of density, I'm going to have to bump up my technical factors. Anatomic part thickness or tissue type. So as the anatomic part size or thickness increases, more photons are absorbed by the part and fewer photons reach the IR. Therefore, IR exposure or density decreases. As the tissue thickness increases, going like from soft tissue to bone, the part absorbs more photons and less photons reach the IR. Therefore, there's an inverse relationship between tissue thickness or type and IR exposure or density. So when we think about these two different things, so take a patient that perhaps was of a sthenic build, okay, with your average size. And I used a certain manual technique, a certain kilovoltage with a certain mass. And let's say I was doing a KUB and that worked. It gave me a good amount of exposure, a good amount of density. Well, now I have a hypersthenic patient coming into my room. I cannot use the same kilovoltage and mass value for the hypersthenic individual. If I did, I'd get a light image. For that hypersthenic patient, I'd have to bump up my technique. As far as tissue thickness is concerned, why does bone appear lighter on a radiograph than the surrounding soft tissue? Because bone has a greater thickness, it's got a higher atomic number, and therefore it is going to absorb more photons. So as the anatomic part size or thickness increases, think about going from a sthenic to a hypersthenic, or as the tissue thickness increases, think about going from soft tissue to bone. You're going to have to change your technical factors to maintain density. Radiolucent contrast media and radiopaque contrast media, we use it to see parts that we would not otherwise see if we didn't use them. For example, if I did a KUB, I might see a little pocket of gas or some feces that might be within the colon, but I'm not going to get a good view of the colon. So I'm going to have to put contrast media into that colon, giving the colon contrast that wasn't already there. When I look at this image here of this double contrast study of the colon, I can see that Those white areas within the colon is barium. Barium's doing what? It's absorbing the radiation, not allowing the photons to get through, creating then less density. And the air or carbon dioxide is going to allow the photons to pass through more easily, and therefore you're going to be having those areas darker on the image. Down below we've got a picture of a cast there, right? Casting material absorbs photons and therefore decreases IR exposure or density. So in order to bring up the IR exposure or density back to the level that we would need it to be, there is a couple of rules here. Dry plaster, you would either double the mass or you'd increase your kVp by 10. If it was wet plaster, it was first applied, you'd have to triple your mass or increase your kVp by 15. Or if it's a fiberglass cast, which is the type of cast that we usually use today, we see being used more often, we'd increase our kVp by about 5 or 6. One thing I want to note there is both those dry and wet plaster techniques, notice the word or is bolded in both. You do one or the other. You double the mass or increase kVp by 10. You wouldn't do both. Okay, same thing for wet plaster. You wouldn't triple and add 15. You'd either triple or add 15 kVp. As far as grids are concerned, what is the whole purpose of a grid? Well, the purpose of a grid is to absorb scatter. Okay, grids absorb scatter, which otherwise would add exposure to the IR and density to the film. So the more efficient the grid is, which you've heard about, we've talked a little bit about grid ratios. The more efficient the grid is, we're increasing the grid ratio, like going from a 5:1 to a 6:1 to an 8:1 to a 10:1, 12:1, 16:1. As I'm doing that, I'm increasing the grid's efficiency, which means it's doing a better job of getting rid of scatter. So the more efficient the grid is, the less will be the IR exposure or density. For example, as I was just saying, a 16:1 grid would absorb more radiation or scatter than would a 5:1 grid. So we want to keep in mind then that as grid ratio increases, increased mass would have to be used to compensate. Why? Because what does a grid do? It gets rid of scatter. And even though scatter isn't good density, it's still density. So if we get rid of the scatter in order to maintain a certain level of density, I'd have to bump up the mass. As far as pathology is concerned, we've got certain conditions that are referred to as additive conditions and certain conditions that are referred to as destructive. Additive conditions are things that add to the body, like fluid. Fluid is going to absorb photons. If we absorb the photons, less photons get to the detector, therefore it decreases IR exposure or density. So with additive conditions, you're going to have to bump up your technique in order to maintain IR exposure. And with destructive conditions like osteoporosis, this is taking away from the body. Like in osteoporosis, we're taking calcium out of the bones. This is going to decrease on the absorption of the photons, which would increase your density. So if you have a patient and they have a destructive condition, you're going to have to make sure that you alter your technique because you have to realize then the photons are going to get through easier, right? So you'd have to decrease your technical factors.